Alright, so for problems 17 and 18, we're supposed to construct a truth table for each of the following. Alright, so the things you need to know to construct a truth table is, first of all, how many component statements do you have? This will tell us how many rows we need to put in our truth table. So notice we have a P and not P, which is still just P, and not Q, which is just Q. So you only have components P and Q. So when you calculate your rows, it's just going to be 2 to the second power, where this number right here is how many components we have. We have 2 components, so 2 to the second power is 4 rows. So when you create this, you're going to need 4 rows. That would answer the question, 4 rows. Really, there's going to be 5 because I'm going to build a header row when I do my problem. On the other hand, columns. How many columns do you need? Well, you need a column for P. You need a column for Q. Of course, you always need a column for your components. But notice also in the problem, we have a not P and a not Q we're going to need a column for. Then you need your parentheses statements. There's only one set in parentheses here, so not P or not Q. And then finally, you need the whole statement in a column as well. So when I build a table for this, or draw one out, doesn't matter, I'm going to need 4 rows plus 1 for the header, so 5 rows, and 1, 2, 3, 4, 5, 6 columns. So magically I put a table down here for us that has 5 rows and 6 columns. So let's fill in everything we need. And I'm going to change my pen for you. Alright, so here we go. I need a column for P, and a column for Q, and a column for not P, and a column for not Q, and then a column for not P or not Q, and then finally the whole statement, which is P and, try that again, P and our set of parentheses, which is not P or not Q. Now when I fill this in, remember the truth value for P is where you want to go first. Now, formally, how do you fill this in where you don't miss any possibilities? Well, take your 4 rows and split it in half, which is 2. So that means I need to put 2 trues and 2 falses in my column. Then you take 2 and split that in half, and that's 1, which means I need to alternate true, false, so 1 of each, and then true, false again until you finish everything in the column. Now, we've got it all set up, okay? So this is every possibility. True, 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 false, false, true, false, false. There's no other way you could organize 2 component statements, truth value. Now, to do not P, remember, you just negate everything in P. So not true is false, not true is false, not false is true, not false is true. Now I'm going to negate Q, so I'm looking at my Q column only, and I'm just changing the truth value. So this true turns into a false, this false turns into a true, this true once again turns into a false, and this false is true. Now we're doing an OR statement. Now remember, for an OR, you only need one of your values to be true for the answer to be true. And I'm looking at the not P and not Q columns only. So when I do false and false, that's the only time we're false, because a false and true is true because this component is true. A true and false is also true because, again, the first component is true, and a true and true is true. Now in the end, the last column, I'm looking at P and my set of parentheses. So way over here, the P column, and right here, the set of parentheses column. Now remember, an AND statement, as a matter of fact, no, we haven't done an AND statement in this problem. I take that back. An AND statement has to have both truth values to be true. Otherwise, it's false. So this first row, true and false, is false. True and true is true. False and true is false. And false and true is false. So it looks like the second row, which means if P is true and Q is false, you get a true statement. Otherwise, any other truth value combination gives you a false statement. So this whole answer is our truth table for this particular statement. And let's get on number 18. We're supposed to construct a truth table. So to do this, we need to figure out, once again, how many rows and how many columns should we have? So when you look at the rows, remember it's always going to be 2 raised to the number of components. Well, what components do we have? We have a p and a q and a p and a q. Look, I only have p's and q's, so it's 2 to the second power, which is 4. Now, the number of columns is very dependent on what you have in your statement. So we definitely need a p column and a q column, because those are our 2 components. Notice I also have a not p and a not q. Just like the last problem, we need both of those represented. And then I have my set of parentheses here, p and q. But notice it gets negated, so then I need a separate not p and q. And then over here I have my parentheses not p or r, so I have an or. And then I have the if-then statement, so that's the final, the whole statement. So notice it gives me 1, 2, 3, 4, 5, 6, 7, 8 columns. So when I build my table, I need 4 rows plus the header. Okay, so 5 rows and 8 columns. So I'm going to do a 5 by 8. But now, again, if the book asks you the number of rows, it really is just 4. When I add that header, that's just personal preference, because I like that top row to be able to list everything that goes in my columns. And magically I have a table here that does have 8 columns and 5 rows for me. So let's fill in our header row up here with all of our column headings. So I have a P for sure and a Q. And then we have a negation of not P and not Q. Pretty standard for a lot of our truth tables. But then I have my set of parentheses P and Q. But then I have to negate that. So not P and Q. Notice you can't do more than one thing at a time. Always do a column for every little thing. And then I have a set of parentheses over here for not P or not Q. And then finally I have the if-then statement. So I'm just going to put the if-then right here, and then we'll note what rows we're using or what columns we're using to do that. Okay? So let's fill in. Let's fill in with purple this time. So my P, again, I have 4 rows. So that means I split 4 in half and I have 2. So 2 trues along with 2 falses. And then I split 2 in half and I have 1, which means I alternate true false all the way down. 1 true, 1 false, 1 true, 1 false. Now not P, I'm only looking at the P column, and I do the opposite. So not true is false, not true is false, not false is true, not false is true. I'm going to do the same thing with the not Q column, but looking at the Q column, of course. So not true is false, not false is true, not true is false, not false is true. Now next I have an AND statement. So I'm doing AND with P and Q only right now. So P and Q, true and true is true. Remember, ands, they must both be true to be true. So when I do the next row, true and false, that's false. False and true is also false, and false and false is false. Now I'm negating that. Notice the not P and Q, I'm only looking at the P and Q column and changing the sign. So this true turns false. The second false turns true, third row false turns true, fourth row false turns true. Now I'm looking at completely separate set of parentheses, this right here, not P or not Q. So I'm looking at the not P column or the not Q column. What's good about ORs? ORs are only false when both of them are false. That's the first line we have, so that's false. But now I have a false and a true, which is overall true, because if one of them is true, it's true. So true false is also true, and true true is true. Finally, I have an if-then. Now for my if-then, notice I'm starting with the not P or Q, so that's here. Does that imply not P or not Q? And I said this wrong. This is not P and Q. And does that imply not P or not Q? So I drew my arrow. Remember, false implies false is overall true, because if you start an if-then statement with false, the answer is true. True and true is true. True and true is true. True and true is true. Turns out this was a tautology. So it doesn't matter what our original statement's truth value was. No matter what, this is true. So our compound statement is true no matter what. So for 19 and 20, we have true or false. Now, a problem like this for true or false, if you can find what we call a counterexample, any particular situation that makes the statement false, then it's false, right? If you can find just one situation where what it is saying is not true or false, then your answer is false. If every single possibility that it sets you up for is true, then you're talking true. So it says some negative integers are whole numbers. So let's get a negative integer. So for example, -2 is a negative integer. Is that a whole number? No, it's not, right? Remember, whole numbers are 0, 1, 2, 3, 4, 5, 6. It turns out there is no negative integer that's a whole number. What's the thing about whole numbers? It's 0 plus all the counting numbers. And none of those are negative. So this is definitely a false statement. We found a counterexample. Example is -2. It's a negative integer that's not a whole number, but it does just say some of them. So really, this counterexample over here, logic-wise, doesn't really work exactly, because if we could find a negative integer that is a whole number, we could say this is a true statement. And there is no negative integer that's a whole number, because all whole numbers, we said, are 0 plus the counting numbers. So sometimes logic-wise, a counterexample doesn't exactly apply when you have these existential quantifiers like some. Now this is an all. All irrational numbers are real numbers. All irrational numbers are real numbers. Now if we could find an irrational number that's not a real number, that's where a counterexample works. So counterexamples work really well when you have all statements or none statements. And this is an all statement. Can we find an irrational number that's not real? Now I'm going to tell you the truth. Numbers that are not real are called imaginary, like 2i, or that's, the square root of -4. That is 2i. Now you may not know anything about those, but the irrational numbers don't fit in that category. These are not irrational numbers. An irrational number might be the number pi, which is 3.14, and that decimal continues forever, or say the square root of 2, which also has a decimal that continues forever. It's a infinite decimal out there. Those are irrational numbers, and those are all real. Matter of fact, the definition of real numbers is all of the rational and irrational numbers. So this is a true statement. And really, this just depends on your knowledge of number systems. And we talked about it in the first chapter that we did in this class, which was just dealing with sets. Notice the directions for 21 through 24. Write each conditional statement in if-then form. So they tell us that all integers are rational numbers. Now, the trouble with writing something in if-then form is you really have to be careful about picking out your antecedent, your first thing, and then your then, which is your consequent, your second thing. This says all integers are rational numbers. So I think it's safe to say if it is an integer, then it is rational, or I should say it is a rational number. It'd certainly be okay to say it is rational, but if I want to be very clear, if the number is an integer, then it is a rational number. Does that mean the same thing as all integers are rational numbers? I would say it does. So when you write it as an if-then statement, definitely go back and look and see if it reads the same meaning as the original statement. But I know this can be challenging. It is for me, because we're dealing with words instead of math. 22, being a rhombus is sufficient for a polygon to be a quadrilateral. So this is one of those, is sufficient for, but this really is an if-then statement. So you could say if the figure is a rhombus, then it is sufficient that the figure is for a polygon to be a quadrilateral. Let me say this more clearly. If the polygon is a rhombus, because it calls it a polygon, you could say the figure though. So if the polygon is a rhombus, then the polygon is a quadrilateral. What do you think? If the polygon is a rhombus, then the polygon is a quadrilateral. That's a classic if-then statement, but it is sufficient for, okay, the sufficient side is your then statement every time. There's some hints in the textbook when you rewrite conditional statements as just any statement as an if-then statement. So go look that up if you're struggling with that. By the way, to help you out a little bit, that list of helpful hints about writing if-then statements is on page 117 in section 3.4, and the title of section 3.4 is the conditional and related statements. So it's all about if-then statements. It's also got the inverse and converse and contrapositive in there. Number 23, being divisible by 2 is necessary for a number to be divisible by 4. Now, this is, to me, one of the more confusing ones. And if I read you information, again, from page 117, about changing a conditional statement to if-then form, it says that Q is necessary for P. Let me write that down. So Q is necessary for P. Now that's writing an if P then Q statement. So it says being divisible by 2. That's got to be our Q statement. Is necessary for a number to be divisible by 4. That's my P statement. This is one of those backwards ones. So we can say if a number is divisible by 4, then what? My Q statement. The number is divisible by 2. You could also write this where it makes sense. So if a number is divisible by 4, then it is divisible by 2. But the other way around does not make any sense. If a number is divisible by 2, then it is divisible by 4. That's just not true. 6 is divisible by 2, right? But it's not divisible by 4. On the other hand, if a number is divisible by 4, for example, 12 or any other number is divisible by 4, I promise you it's also divisible by 2. So think about it logically too. I mean, use the tricks as needed. I do, especially when I do problems like this. But read it and make sure it has the same meaning as the original statement, and make sure it's a true statement. That doesn't always apply, because sometimes you can't tell if it's true or not depending on what's going on. But if it's mathematical, you can certainly check it. And then the last one of these, 21 through 24, we're supposed to write this as an if-then statement. So she digs dinosaur bones only if she's a paleontologist. Now, this kind of gives it away. If she's a paleontologist, that's your if part, right? So if she is a paleontologist, I'm having trouble writing, then she digs dinosaur bones.